Okay, let us begin 2019 paper 2 with, of course, module 1. The first question, we're given a compound here and we must name this compound, right? Also, it reacts with sodium hydroxide to produce an alcohol. So, because it's reacts with sodium hydroxide to produce an alcohol, we already know that it is a halogenoalkane. Based off of its structure, we have on the first carbon, well, we have two carbons there, right? It's a branch chain there. So we have one, two, right? On the second carbon, we have a methyl group. We have a bromine there. There's a methyl group attached to that carbon and two other carbons here. What would be the name of this compound? What would be the name of this carbon compound? Oh, it's not a carbon compound, my bad. This organic compound. Any suggestions at all? You can't name it? I am getting nervous because why am I not getting any responses? Most people say, mm-hmm. Okay, 3 bromo 2 4 dimethylhexane. All right, lovely. Let's try that. Somebody said 2 3, so let's provide the structure and see what comes up there. All right, so we have to be able to read the entire structure. The first thing that we see methyl groups, right? A methyl group, and then we see two here. So that would imply, I guess two carbons here, right? So we're just looking at that. So it could have been something like a branch chain that we're looking at here. Two methyl groups there. Then we have another methyl group. So we have CH3, 2. Hold on, let me just these persons into the meeting. Alright, so we have CH3, two CH3, so two methyl groups basically. Alright, so it's something like that. And then we're gonna have on one of the carbons, we're gonna have a bromine. Let me just draw another structure. So that's one, two, three. On a carbon, we could possibly have a bromine. Remember, if we disagree, we can state that. Then we're gonna have another methyl group attached to another carbon, right? And then two other carbons coming out here. All right. So looking at this, do we have the correct number of carbons here? All right. So we're trying to get the actual name from this compound here. All right. So we have a methyl group. Go ahead. Yes. Just. All right. So we're just looking at this, right? So we have the methyl group. We have two of these. Then we have one carbon, then another carbon. All right. We're gonna have this here. So let me let me just ask specifically, right? With this part of the structure, right? This implies that the bromine is attached to this carbon, all right? Does it also imply that the methyl group is attached to the same carbon? That's my first question. Yes or no? It does. Okay, so let's look at this. So methyl group is attached to the same carbon there, and then we have three other carbons out there like that. So if we have something like this, what would be the name of this compound? Because we're saying it is 2, 3. What was our response? 3 bromo, 2, 3 dimethylhexane. So we're saying it's 3 bromo, 2, 3 dimethylhexane. Alright. How? Mm, or 2, 4. Oh, it's because someone has in the chat 2, 3. And we have 2, 4. Okay. So, how do we arrive at the bromine on third carbon? Alright, but based on what I have here, whether any change that you count, right, you're going to end up on the fourth carbon. So is there something fundamentally wrong with how this molecule is drawn? Yes or no? Anyone? We're saying it's 3 bromo. Both two persons say it's 3 bromo. So that means that there's something wrong with the molecule drawn here. Can you guys point it out if anything is wrong? Not hearing any responses. Is there something wrong here? Do I need a double bond between carbon 3 and carbon 4? Okay, let's have a look at that. So we're gonna have CH3, alright? So we're gonna have two CH3. So if you could look at this, this would be, for example, CH3 here, right? We need another CH3, right? So we could imply now, what would we could we imply about this now? That both of them are methyl groups, right? Because if we have this carbon down here, it would be a CH2, so that wouldn't be the case. So we're saying here on this first carbon, right, we have the potential for two of these groups. Let's have a look. All right. So the potential for two of these groups. Let me erase this. All right. So if we have two methyl groups there, on this carbon it only has one hydrogen. So that would be the CH, right? Connected to a carbon containing a bromine and a methyl group. So let's shift it over here. So containing a bromine substituent and another methyl group. Right, so I have something like that. And then we have three other carbons in the chain going down. Alright, so how does this look? Does this make more sense? We have one, two, three, four, five, six, seven, eight. So in the first carbon, there are two methyl groups, right? On the second carbon here, in this chain that I'm talking about here, there will be a bromine and a methyl group, and then there are three other carbons. So how would we name this compound? We'd name it from this direction, right? So one, two, three, four, five, six. All right. Longest carbon chain first, and we always number the carbon chain from the most important or the highest priority group that we have, which is in this case would be bromine. All right. So look at something like that. So on the second carbon there is a methyl group, right? On the third carbon there's a bromine substituent and another methyl group. And the longest carbon chain contains six carbons. So what is it called? It is 3-bromo. Mm-hmm. Lovely. All right. The 2,3-dimethylhexane. State the type of reaction which takes place when the compound reacts with sodium hydroxide. So it says in A that it reacts with sodium hydroxide to produce an alcohol. What is the name of that type of reaction? Anyone? It is a substitution reaction. Okay. So it's a substitution reaction. Let's start there. It's a substitution reaction, right? That's a type of reaction it is. The mechanism, right, is different from what the reaction is, right? So it's a substitution specifically of what? SN2 or SN1 origin? Is it SN1 or SN2? SN1. Why would you assume it is SN1? Okay, lovely. Right, so it's a substitution reaction by the mechanism, right? That we're talking about would be SN1, right? So specifically, it's a nucleophilic substitution. It's an N substitution, right? Or nucleophilic substitution, right? So we have that there, that's fine. Number three, or part three now, asks us to outline a mechanism for the reaction using curved arrows to show the movement of electrons, show clearly the structure of any intermediates formed, as well as the final product. So how would that reaction occur? So looking for the nucleophilic substitution of a tertiary halogen alkane. Mm-hmm. All right. So let's have a look at this. So for the, you sure this is SN1 or SN2? Which one? Okay. So for the tertiary halogen alkanes, we would prefer the SN1. And with the SN1, we create a carbocation intermediate. Yes or no? Lovely. Right, so we won't create that type of molecule that is flowing between the two states, right? So let's have a look at this. So let's quickly draw our type of mechanism outlining this reaction. Now, I am not going to draw everything, right? I am simply just going to write R, right, and a R here. I have a carbon there, and another R here, and then we have the bromine, right? So we have something like that. Or I could flip around these two to put the bromine right here. It's technically an isomer, but let's look at this. Alright, so let's flip this around. Have the bromine there, have that R group here. So those are methyl groups, right? So as we stated, we're going to have homolytic fission. Heterolytic. Lovely. Thanks for catching that. Alright? So it's heterolytic fission as both electrons flow onto one of the atoms. Alright? Because of its electronegativity. That will be the first part, and this is now the formation of the carbocation intermediate. So we're going to end up with a tertiary carbocation, of course, because of a tertiary halogen alkane. Alright? Gonna end up with something like this. Now, it is important to note that we have a preliminary step before we reach here. What would the preliminary step be? The preliminary step would be the autoionization of our sodium hydroxide. So we know we have our sodium hydroxide, and we know that we're going to form an equilibrium between sodium ions and OH ions. Right? So we know now that we have created the proper conditions for having the hydroxide ions in solution. So from there now in our mechanism, we'll have the hydroxide with two extra electrons there. Alright? And it is these electrons that will go to the carbocation intermediate here. Are we following so far? Does this make sense? So from this step, we're going to now gain the tertiary alcohol, right? So we're going to end up with R groups on all sides here and a hydroxyl group there. That is it. There's nothing more to it. But we must make sure that all the arrows make sense and they're going in the right direction. How many marks is this? 3 marks. This is easy. Alright? So that is that. We can move on. I'm guessing we can move on. So let's move on. Go ahead. I would say yes. And to be very honest, there are going to be some persons that say, "Oh, you don't have to." But no, For me, definitely you put it right. There's no universe in which I won't put it. Right? It's just something that I normally do with all reactions. I put up the creation of these ions that I will have in our entire thing, right? So to be very honest, right, whether or not CAPE requires you to put the equation, put the equation. Right? That's my thing. Right? That's my suggestion. But the equation is there. You have to create the intermediate. Right? That's what I would do. It's a general rule of thumb. It's good practice. Because if we're looking at something like the nitration of benzene, look at nitrobenzene, this question here, I will definitely state that you must have your reactions that come before the mechanism, right? For the nitration of benzene, what are the reagents that we use? What? Okay, so we have nitric acid, HNO 3, right? Then we're gonna have what else? H2SO4, right? What else do we have? The conditions would be what? Would it be glacial conditions? It wouldn't be glacial because this is not creation of phenylamine. So it would be around 50 to 60 degrees Celsius or so, somewhere around there. All right. Do we have a catalyst for this reaction? The catalyst is the acid, right? H2SO4. So outline the mechanism described here. What's going to be our mechanism? This is the nitration of benzene. I must be able to do this. Lovely. So I'm just writing down the steps here, and then we just drop the reactions underneath them. Right. So there are three general steps that we're looking at. We are looking at the formation of nitronium ion. We're looking at the electrophilic aromatic substitution, right, with deprotonation and protonation in mind, right? So you're gonna specifically have deprotonation after. So you're gonna have the addition of the electrophile. So part one of this would be the addition of the electrophile of the electrophile there, right? And then we're gonna have the formation of the sigma complex, right? So that would be the first part of this. Okay, so we're gonna have that. Then we're gonna have potentially the next step would be the formation of the sigma complex. Alright. And then we're gonna end up with the last step being what? Deprotonation also. Alright. Deprotonation. Alright. So let's go. The first thing, as we were stating before, we're gonna end up with H2SO4 plus our nitric acid HNO3. Right? It is in an equilibrium at this moment to produce what? H2NO3, which will produce now our NO2, our nitronium ion. Alright? Our nitronium ion is going to be what? Positively charged. Have that there. Right? So now we first start off with our benzene. This is terrible, by the way, terrible drawing. Right? We start off with our benzene, and we're going to have our nitronium ion first of all. we're gonna have the movement of the arrows. So the arrows move from electron, right? The electron here to there. Hold on, let me make this a little bit more explicit. Let's draw out the entire compound. Let's draw the O double bond N double bond O. Right, this makes a little bit more sense now. What we're gonna end up with now is the electron moving from the bond there to the nitrogen. And the electron is gonna move from the double bond here now to the oxygen. Alright? This now will produce a complex. Let's look at the production of the complex now. We're gonna end up with a destabilization of the ring, right? Because we had sp3 stabilization, right? So we're gonna have well sp2 stabilization. Is that true? sp2, right? And because it's now sp stabilized, we're going to end up with different complexes. So we're gonna have NO2 here. We're gonna have multiple complexes. Apologies, let me fix that. Alright. We're gonna end up with multiple complexes, and because it is now sp stabilized and not sp2 stabilized, we're going to have the frantic movement of electrons, right? So we're gonna have let me just draw these like this, and then draw the electrons moving using this, right? So we're gonna have a constant movement of electrons around the ring to try to stabilize it, right? So we're gonna have a positive charge there, positive charge there, positive charge here, right? So it's gonna be destabilized. So really and truly, we have a resonance hybrid being formed there. The only way we can stabilize the ring is through deprotonation. So now we must show the deprotonation of the ring, right? So let's draw out everything now so we can steadily show the deprotonation here. So we end up with a bromine ring, not a bromine, benzene ring rather, um, like this. So we end up with NO2 here, and we have a hydrogen here. Not true. Let's put a positive charge here. The electron now from the hydrogen will now move into this positive region, right? And this is all in the presence of water, not true, right? And it's in an acidic presence of an acid. So I have the electron moving from that to this. I think the best thing here is to actually use sulfurous acid or hydrogen sulfide actually, or sulfate rather, to show this. Alright. But we're just moving on with this. This would now produce what? Nitrobenzene, right? We'll produce our stable nitrobenzene, NO2. Alright, so that is the mechanism, but I think I would prefer to use HSO4 here. So let me use HSO4 here. So I would prefer to use HSO4. Right? Electron moving from one to the oxygen in the HSO4. Because that will now reproduce our H2SO4, which is our catalyst. And we see that the catalyst is unchanged at the end of the chemical reaction. Alright? So that is it. Any questions, any concerns, any emotional outbursts? Is there anything that I need to do? Do I need to call an ambulance? Everybody's okay? Guys, I'm okay, lovely. Because I was about to say that I'm not getting the responses and it's making me nervous. Alright, so lovely, that's that. There shouldn't be a lot of problems. Very easy for the prepared student to do, especially for the module one. Alright, next question now. C, right? A synthetic route, can everyone see the screen? Okay, lovely. So a synthetic route from nitrobenzene to compound E is shown. Now this, right, was my bread and butter. This is really good, right? It's a really great question. And those who know that this is a really great question, right? So what's happening here now? So we have nitrobenzene to phenylamine, right? They will provide a salt, a diazonium salt to be specific. And they will end up with an azo compound. Lovely. What's the name of reaction one? My apologies. The reagents. I thought it said to name. My apologies. Tin and HCl? Or would we just fling it into an HCl and that is it? Are we sure? Do we agree with this response? Alright, so no, well, we're going with this. Tin in the presence of hydrogen. I am saying hydrogen chloride. Um, oh my gosh, I was about to say chloronic acid. It's hydrochloric acid. Yes, that's lovely. Part two now. What are the reagents for that? All right, lovely. So the first one is the reduction. I'm gonna put the name regardless. This is diazotization, right? And we require the sodium nitrite rather. And we require HCl, right? HCl. Mm-hmm. That should be fine. Everything there is good so far. Everything here should be good so far. All right. And we know that diazotization occurs at glacial temperatures, which is going to be 0 to 5 degrees Celsius around there, or 5 to 10. Part last one. Last one, this is called the hydrolysis of the phenol. What do we do to the phenol? Are we sure? Are we sure? The formation of the azo compound, or the azo dye, we're sure. That's what we need. Okay. All right. So we're reacting this compound. Now remember that we started out with this, right? Reacting that compound with a phenol, all right? And we're also reacting it in the presence of sodium hydroxide, right? Would it be glacial temperatures as well? I mean, that's not necessarily okay. It would be glacial temperatures as well. All right. So that should be fine. That should be fine. All right. So everything there should be okay. State the class of compound to which E belongs. What's the class? Which class of compound E belong to? A is a compound. All right. I'm giving what is the commercial significance of azo compounds? Dyes, textiles. It can be used to create what else? I mean, that's fine. It's 2 marks I ask for. But it's usually dyes the syllabus want us to look at. Consider the statement all amines are weak bases and aqueous solutions of amines are basic. Consider that. Use the compound ethylamine and a relevant equation to explain the statement above. Are all amines basic? Let's look at this. So ethylamine is a weak base in water, not true? Yes or no? Let's show this. Did I just put plus NH2 a while ago? My apologies. That's bonded together. Um, NH3 plus OH. Alright? So seeing now from that equation that demonstrates the weak basicity of this compound. So the lone pair and the light nitrogen act as a proton acceptor, forming hydroxide ions and making a basic solution. Not true? Are we following? Sure. I don't like the response. Sure, no. But I guess so. Yeah, but that really explains that there, right? So you can use just the proton acceptance, right? In order to form hydroxide ions. So this is showing not only Bronsted-Lowry acidity, but it's also showing Arrhenius as not acidity, Bronsted-Lowry basicity, but Arrhenius basicity, right? So it shows that ethylamine can display those two, all right? So you just need to explain the statement above. So explain why these amines are weak bases, right? You must be able to explain those things. The nitrogen has a lone pair of electrons, right? It can donate those pair of electrons, i.e. it's a Lewis base. Or it can accept a proton, i.e. it's a Bronsted-Lowry base, right? We're looking at stuff like that. Must be able to explain it. Go ahead. It will. I would still consider it a weak base. It may not be as weak really as it relates to other amines, right? It may be a stronger base relating to other amines, but by mere fact that it's an organic base, it's a weak base. All amines are weak bases. Some may be stronger than some, but all are weak. Same thing with the organic acids. All organic acids are weak acids, but some may be stronger than some. Right? So yeah, so it is still categorized as a weak base, but it may be stronger than some other bases, some other organic bases rather. Right? But you could explain that as well. Explain the alkyl groups and how it increases the availability of the electron lone pair on the nitrogen, right? And speak about how that electron will interact with other species in a basic way. See, that's a double entendre. Basic, same thing. Right? Alright, so let's look at this. The pKb values of ethanamide, ethylamine, and phenylalanine are 14.51, 3.27, and 9.38 respectively. Account for the differences in the pKb values. What are the differences in the pKb values here? So for rank them, ethylamine has the lowest pKb, then phenylamine has 9.38, then ethanamide has the 14.51. So the strongest base here is ethylamine, followed by phenylamine, then ethanamide. So as we stated first with the ethylamine, right? The alkyl groups don't need electron density, increasing the basicity of the compound. Not true? Can we agree with that? Lovely. For phenylamine, the lone pair, right, the lone pair of electron is delocalized into the benzene ring, reducing the basicity. Not true? So the lone pair of nitrogen participates in the ring. hmm So it makes it weaker than ethylamine rather, but it is still stronger than ethanamide because with ethanamide, the lone pair on the nitrogen is delocalized into a carbonyl group that has resonance conjugate stability. So that makes it even worse, even less available if it is in a carbonyl group. This is a 2019 paper. Alright? So looking at stuff like that. So are we able to explain these or do I need to write something on the screen? I don't know. Ethylamine? Alright, so the structure for ethylamine. Okay, so I'm going to write out something, but let's draw that structure then. It's already in this question here. We have that, alright? But ethanamide, right? Ethanamide would be, let me put it in blue to differentiate it. I'm going to put it on the same place up here. Ethanamide would be CH3, CH2. Oh, what would be an amide? Amide, what's that linkage? What's the amide linkage? Excuse, repeat? So the amide linkage, let me erase that here, right? Because this is ethanamide, is going to be something like this. We're going to have a double bond, also we're going to have a carbonyl, right? So that's ethanamide. So as we see the carbonyl group, we know that this is a resonance stabilized compound, and we must be able to tie that into the basicity. All right. So let's go with this here. All right. So let's look at this. All right. So we're saying that ethylamine, right? The alkyl groups donates electron density to the nitrogen, right? Increasing the basicity. Somebody's trying to join the meeting, so increases the basicity there, right? With the phenylamine, what happens with the phenylamine here? Lovely, right? So it would overlap, or it would participate, or it would become delocalized into the benzene ring system, right? And that makes the electron less available, right? So it reduces the basicity. But with it, the ethanamide, right? Same thing, Same thing about the lone pair and the nitrogen, right? The lone pair of nitrogen now participates in resonance stability in the carbonyl group, right? This makes it the weakest of the bases. All right. So looking at stuff like that. Alrighty. So we can now move on with our lives. All right. This is a fairly simple paper. The table shows some reactions of phenol. Complete the table by inserting the appropriate observations and reagents. Right? And for those who know me know that I love types of tables like these. Best things ever. Alright. The phenol producing this compound out here. So looking at a compound out here where the hydrogen, right, is replaced with sodium. Right? What would be the reagent we use for that? Sodium hydroxide. Alright. So using sodium hydroxide. Because remember the phenol is slightly acidic, not true. So it will have that neutralization reaction. Sodium hydroxide. Alright. For the phenol giving us tribromophenol, right? Which is going to be, or what? That would be what? 1, 2, 3, 4, 5, 6. 2, 4, 6 tribromophenol. I would say it's Br2, 3. Okay. So 3 bromine. I mean, sure. Yes, yes, yes. Right? And we're gonna end up with that now. What are the observations? Observations for tribromophenol. We're going to not only get an antiseptic smell, boy, antiseptic smell, right? But we're gonna also have a yellow precipitate, a yellow brown or a golden precipitate, right? Gonna end up with something like that. For the last one, we're gonna end up with an acyl type of compound. Isn't technically not acyl, right? But let's have a look at that. What would that be? What are we adding here? We're gonna react phenol carboxylic acid to get that. Hmm. Is that an ester group acid there? So gonna react a phenol with a carboxylic acid to get an ester. Alright. Are there any objections to this? Mm-hmm. Alright, so or why? So the slide that I would put pale yellow, right? But is it that you're more comfortable with white? Have you been seeing white as a precipitate for this? White? So if I were to be more specific with this, I would put pale yellow, right? But I'm not really sure about white. I've never really seen white as the precipitate for this. Um, but I'm guessing that if this is low, it is the concentration is low enough, it can appear as a white precipitate, right? So that can be justified. For the last one, we're reacting the phenol with carboxylic acid. Phenols don't typically react with carboxylic acids, that's what I'm trying to like figure out. They do not directly react with carboxylic acid to produce esters like that. But this is some type of aspirin. This is aspirin actually. Hold on. I never noticed that. This is basically creating aspirin. Right? With that production you will need probably ethanoic acid. But they don't typically react directly like that though. So for something like this, we'd primarily use something like a sodium hydrogen, well, not sodium hydrogen carbonate, but we'd probably oxidize it to become a carboxylic acid, and then we add a sodium hydrogen carbonate or something like that to get a type of ethyl benzoate kind of thing. All right, but they don't typically react with carboxylic acid directly like that. So on to module 2.